Hello everyone. In this video, I will demonstrate how to perform exploratory factor analysis. Exploratory factor analysis is often used as one of the techniques to perform data reduction. So if you have many variables and you want to see the underlying structure or represent those many variables using few components, you perform exploratory factor analysis. And in this video, I will demonstrate taking the actual case and showing you how to do that in SPSS. So the data set I'll be covering in this video is this one here. It relates to various countries. So we have the data on many different countries. Each case is one country, and we are recording for every country: male life expectancy, female life expectancy, births per 1,000 individuals, infant mortality rate, fertility rate per woman, natural log of doctors per 10,000 individuals, natural log of radios per 100 individuals, natural log of telephones per 100 individuals, natural log of gross domestic product, and natural log of hospital beds per 10,000 individuals. Now all these are natural logs. So I have already performed the transformation because these variables were not normal. So in order to make them normal or normally distributed, I took the natural log of that. So I will not cover that portion here, but I just want to make it sure that you understand why I took the natural log here. This material I'm basically referring from this book here. It's a Craig Mutler's book, very good book here. Advanced Multivariate Statistical Methods, 6th edition. So if you get a chance, please read through this book. A very good book for multivariate data analysis. So coming back to our example here. So we have many different countries. If you see, we have almost 122 different countries, and we have all those 10 variables. So we have these 10 variables, and we want to see if there are any underlying structure that exists for measures on these following 10 variables. So coming back to our example here, when you're doing the factor analysis, the first issue you need to deal with is the sample size. Now, the general rule is for every variable that you have in the data set, you must have at least 10 cases. So if you have 10 variables, then the good size for the data set will be 100. And if you have 20 cases per variable, that would be very good. In other words, the bigger the data set, the better it is. The minimum requirement is often like 1:5. For example, for each variable, you need to have at least 5 cases or observation. So if you have 10, then at least you need 50 bare minimum. But as I said, the bigger the better. The more generalized rule is you need to have at least 10 or 20:1. Like for every variable, you need to have 20 cases. That's going to be very good. It will give you more reliable results. So that's about the sample size. And looking here, we have not that big a sample. We have 10 variables and 122 records. So some of the data on some countries are missing. So probably we might have around a 5:1 ratio, 5 cases for every variable. But we will see there. But this is our sample size here. And once the sample size is taken care of, the next thing we need to deal with is the missing values. Now, to see how many cases are missing value, what I'll do here, I'll go to the Analyze Descriptive Statistics, Explore, and I have already chosen those factors here. Those are the 10 factors here. I can choose it again. So from here, and I'll just select all these things and put it back here. Statistics, I just want to do the descriptives here. Plots, I'm not interested in any plots right now. but I need to choose bare minimum histogram here, which is selected here. I'm not doing any box plot, nothing here, and I'm just gonna say okay here. In the options, make sure you understand this exclude cases list-wise. What this means is, while exploring the data set, only cases with complete values will be explored. That's something you need to understand here. Continue here. So basically, this is the table I'm interested in right now. I'm not going to go through the histogram. That will be the case when we're going to start discussing the assumptions. But here in general, it tells me that data set has 105 cases or 105 countries for which we have complete information. And there were 17 countries for which we had some values missing for those 10 variables. So it's like 13.9% of the cases have some sort of missing values. So we're gonna ignore those missing values in this data set, but often for 13 to 15% missing values, you perform data imputation. And what you do in data imputation is you replace the values with some sort of expression. So in case of metric variable or interval scale variables, you replace the missing value with either mean or median, depending on which is more applicable. And if your variable is categorical and having missing values, then you replace values using mode or most frequently occurring categories for that variable in the data set. So we're not going to deal with that. That's something for your information here. So here we are done with the missing values. Next thing I'm going to do is I'm going to move on to the outliers. Now, as you may know, factor analysis is kind of very much affected by outliers. So we need to make sure that we satisfy those conditions here. Now, outliers can be done on a univariate level for every variable separately, but we are more concerned about multivariate outlier because this is sort of multivariate data analysis here, factor analysis. So we're not worried about the univariate outliers. We are more worried about are there any outliers when you group all these variables together, because that's what we're going to do here. Now, how multivariate outlier works. So what it does, you have 105 cases for 10 variables. So it's going to form one global centroid for all this complete data set. And then from that global centroid is going to create a center for every case and see how far that center is from the global centroid. If it is statistically significant, then that is deemed outlier. So let's see how we do that here. So I'm going to close this one here. Before I go to the outlier, I forgot to mention another way you can do that, the more detailed analysis for missing values. So I'm going to quickly show you that here. Report, go to analyze report and case summaries here. Put in all your variables here. Statistics, we're not going to do any here. Options is going to again we're not going to mention anything here. We're not going to display any values here. We just want to know the basic summary of missing cases. So the results are here. So it gives you variable wise data. For example, life expectancy for male has all the information. So is the female life expectancy. They have all the data. But if you see a phone, a number of phones, natural log of phones data, it has 8 missing values. So it gives you kind of a pattern in the missing value. And if you see overall, I don't see any particular pattern. Looks like the data is missing completely by random, and that's one of the major conditions you need to fulfill. The data, the missing value should be categorized as missing completely at random, and that looks like a pattern here. So we can again you can do the imputation in that case, but in this case we're just going to ignore that. So coming back to outlier now, so I'm going to close this one here. To perform the multivariate outlier, what we're gonna do is we'll go to analyze here, general, let's see, regression here, linear, and I'm gonna put in all my independent variables here. So I'm gonna say birth rate, infant mortality rate, fertility rate here, and all my log values here. I'm gonna put that in independent box. Now, the dependent, since we are performing the multivariate outlier, we're going to be calculating what we call Mahalanobis distance here, and this distance calculation is not affected by the dependent variable. So we can choose any dependent variable you want, any numeric dependent variable you want here. It will not affect your analysis here. Ideally, we should create ID variable and then do it that way, but again, this is not affected. The Mahalanobis distance is not affected by this dependent variable, or it does not matter. So I'm just going to choose something here. Probably I can choose the GDP here. Again, it does not matter. Just I'm going to do that here. Save. We want to save Mahalanobis distance. Options we don't need to here. Again, is going to exclude cases list wise here. Okay, so is going to do the calculation only for complete cases. So remember, we have around 17 cases for the missing values, so it's not going to be done for those. So we don't have anything to do with the style here. So I guess I'm pretty much done here. Okay, I'm going to say, so it's going to go ahead and create additional variable for me. I'm going to say okay here. So if I close this one here, if you go all the way to the end, it has created this Mahalanobis distance here for every case here. Okay, only for the cases where you don't have any missing values. Now I have previously done a lot of analysis, so that's why all these factors are coming in. I'm gonna just go ahead and delete these factors here. Okay, so just to make sure that we are on the same page here. So these are the distance. Now, if I arrange this one, let's say sort descending. So probably it's going to show me all the one that has, these are the cases that are farthest away from the global centroid. So I don't know whether they are statistically significant. So for that, we have to calculate the p-value from the chi-square distribution, and that's very easy to do here. So we're just gonna go ahead and do that. So I'm gonna say transform compute variables. I'm gonna say here probability underscore MD stands for Mahalanobis distance here. 1 minus, I'm gonna use CDF function, CDF chi-square, and while that question mark is highlighted, I'm just gonna go to the last one here, and that's the distance I just created, Mahalanobis distance, MH3, and degree of freedom is simply the number of variables we have that we want to analyze. So in this case, that's 10 here. So that's executed here. So it's calculate. It has calculated all the probabilities for every distance here. I'm going to go ahead and sort this in ascending. So so these are all the values here. Again, 17 cases does not have any. There are 70 cases which have some missing values in them, so those are ignored by default. And this p-value is critical if it is less than 0.001, but we don't have any case that where the p-value is that significant. So we don't have any outlier in this data set, so we have satisfied that condition here. So once you are done with the outlier, again you can exclude these cases here. For example, the cases that have missing values, you can put a filter on it, and that's very easy to do it. For example, I can say data select cases, let's say if condition here. Let's say I can say if the probability is choose only cases where this probability is greater than 0.001 because that's our cutoff, right? And continue here and say okay here. So none of the cases were excluded, but these cases are excluded because they have some missing values. So because we will be performing complete case analysis. Again, this filter is on, it's indicated here. This does not matter here because anyway, when you do the factor analysis, it does complete case analysis by default. So I can just go ahead and go to select cases and select all cases. Okay. Okay. So we are done with outliers. The next step, what we have to do is we have to perform univariate descriptive analytics. So for example, we have certain assumptions while performing factor analysis. So one of the assumptions is each variable must be normally distributed. And the second one is all the linear combination of all the variables must also be normally distributed. And the third one is the relationships among all pairs of variables must be linear. Now, as you may know, we can always check the univariate normality by performing statistical analysis individually on every variable. But when it comes to multivariate normality, it's very difficult to test. So what we're going to do here, we're going to perform the univariate normality distribution test here. But when it comes to multivariate normality, we'll do bivariate normality kind of overview using Scatterplot. So Scatterplot will help us determine whether our variables are normally distributed, and also whether they are linearly there is a linear relationship between them for each pair of the variables. So that could be done using Scatterplot. But let's do first univariate normal distribution analysis here. So we're going to go to the analyze here, descriptive statistics, explore. I already have all my 10 dependent variables here. Statistical plot. I just want descriptive here. Statistics plots. We want I want factor labels together. I want stem and leaf, histogram, normality plots with the test here. Options is going to do is going to exclude cases list wide. That's mean it is going to exclude those 17 cases that have some missing values. It's just going to consider all the cases that have complete information here. So I'm going to do that. Say okay here. So as you know, we have 105 cases that have all the information. 17 have the missing values here. I'm gonna go straight to, let's say, a test of normality here. Most of them are significant, which means that they are not normally distributed. So this is KS test and this is SW test. So most of them are significant. If this is significant, that means our variable is not normally distributed. As I have explained in the beginning of the video, that I'm taking the natural log of this variable, natural log of doctors, radio, phone, GDP, and deaths, because they were not normally distributed. So after taking the natural log, most of them are normally distributed here. So that's the test of normality. Again, they are very sensitive to the sample size. So if you review the literature, you need to be, careful accepting these test results here. But it gives you a good guidance or overview overall. So that just for our knowledge, we're gonna go ahead and do the factor analysis because, as I told you in the beginning, most of the assumptions for exploratory factor analysis are not enforced because we are mainly performing exploratory factor analysis. So if you go to the life expectancy here, histogram, that's the histogram for, it looks like negatively skewed a little bit here. Stem and leaf graph also shows the same thing. this normal QQ plot is not perfectly normal. Had it been perfectly normal, you'll see all the dots lined up across or very near to this straight line here. Box plot also kind of very, like, it's not very abnormal as such, but it does have skewness to the left here. So likewise, you can go ahead and check every variable here. Natural log of phone here looks very kind of, if not normal, but it's very symmetric here, uniform sort of distribution. And you can see that in the box plot as well. That's pretty much acceptable. So this is how you conduct univariate normal distribution analysis. Now let's do the bivariate, because other assumptions are not only the individual variable, but all the linear combination of all variables must be normally distributed, and the relationship among all the pairs of variables must be linear. We cannot do all the linear combination of all the variables for normally distributed analysis, because that's something very difficult to do. But we can always see the scatter plot, and if it is nicely elliptical shaped, we can pretty much guess that we do have bivariate normality and good linearity among the pair of variables. So let's go ahead and do the scatter plot here. What I will do here is I'll go to the graphs here. Chart builder is not working for me. For some reason it's giving me the error. So if you go here, put in all the values, I'm going to show you is what kind of error I get here. So okay, I'm going to type this in here. Let's see over here, it just gives me a lot of errors. I don't know why. So I'm going to use the legacy chart builder. Okay, I'm going to close this one. I don't want to save that output. Graph, legacy dialogues, scatter plot here, define here. Here I'm going to put my variable in the matrix variable here. Let's see, okay, here. Now it gives me this this chart here. So we can always make this chart bigger, draw the regression lines, and also populate the diagonal with the histogram. So let's go ahead and do that. Double click on the chart here. Double click on this chart editor again. It's going to open the properties windows. Chart size, I'm going to say, let's say give me 700. I'm going to make it a little bigger here, which will be easy to interpret. I'm going to draw the regression line across all those data values, which is going to help me see the linearity between the pair of variables, and I will populate the diagonal with the charts here, histogram. So option show charts in the diagonal. Okay. So this gives you a nice little correlation matrix here, scatter plot. For a pair of variable to be bivariate, normally distributed and linear to each other, these should be pretty much elliptical, and they are nicely elliptical here. Most of them are very nicely pretty much elliptical in shape. Again, we transform some of the variables taking the natural log to make it more normal. But here, this is very good in shape. Like we are very much satisfying bivariate normal distribution assumption as well as the linearity assumption here. So with that thing done, the next thing we have to do is we have to go ahead and perform the factor analysis. I'm going to close this in here. So I'll go to the analysis, dimension reduction, factor. I have all those 10 variables here anyway. Descriptives, I don't want univariate descriptive initial solution. I want coefficients, KMO, and Bartlett test of sphericity, reproduce correlation matrix, extraction. I want correlation. I'm gonna to start with. I'll go with the eigenvalue approach. So if the component has more than one uh, eigenvalue, extract all those components. So I'm gonna go with the Scatterplot here as well. Rotation, I want to employ Varimax rotation here. That's orthogonal rotation, which means it's going to produce the components which will not be correlated to each other. They will be orthogonal to each other. So again, the correlation between those components will be minimal or should be none as such. So we do want rotated solution here. Scores, I want to save the regression scores here, so I'm going to save as variable regression. That's selected here already. And for the option, I want to sort my uh, results by size. Again, when you perform the factor analysis, it excludes cases list-wise here. Say OK here. So it gives you this correlation metrics, which are very good to go through to see where most of the correlations are happening. Pretty much most of the correlations are pretty good, about 0.6, some are 0.8, 0.7, they're pretty good, 0.9. So most of them looks like a very good correlations. Now you need to understand that the factor analysis thrives on high correlation between variables. So let's say if these variables are not at all correlated to each other, you might come up with as many factors as the number of variables, which are 10. So if they are perfectly correlated to each other, you're just going to come up with one factor, because one factor should be enough to explain, or in other words, one component is good enough to explain all the variation among all those 10 variables. So the more high the correlations are among the variables, the better it is to form the components while performing the factor analysis. And this KMO and Bartlett test kind of shows that. So Bartlett's test of sphericity is significant, which basically tells me that at least some of the correlations in this correlation matrix are significant. So that's one condition we satisfy here. And KMO, measure of sampling adequacy, kind of measures the shared variances among these variable, or the common variances among these variable. Again, the more shared variances among this variable, the better it is to perform factor analysis. And KMO, measure of sampling adequacy, it ranges from minimum 0 to maximum 1, and should be for this test to be critical, the value should be greater than 0.5. But here it's 0.9, which is a very good value here. So we can go ahead and perform the factor analysis with full confidence. Again, these tests are very highly sensitive to the sample size, so that needs to be kept in mind. And often some of the literature are saying that you don't even need to perform these tests. You can just straight away go to the communalities here, because we are performing exploratory factor analysis. But again, different literature says a lot of different things, so it's always good to look at these results here. Now once you are done with the correlation matrix and KMO Bartlett's test, the next thing is the number of components you want to retain. Okay, now these are the 4 condition or criteria that helps you to determine how many number of components you should retain. If you're using eigenvalue, which we are using that approach here, so components with eigenvalue greater than 1 should be retained. This criterion is fairly reliable when the number of variables is less than 30 and commonalities are greater than 0.7, or the number of individuals or the cases is greater than 250 and the mean communalities is greater than 0.6. But we do have very less number of cases. We only have around 100. So, but we want to make sure that if we are satisfying the first one here. So I'm going to go back here, see we don't have all the communalities greater than 0.7 here. So this is in radio, natural log of radio is 0.5, and natural log of beds is 0.67. They are both less than 0.7. So if you're using eigenvalue, that might not give you a very reliable results, because we are not extracting the minimum limit of 70%. By the way, what do you mean by communalities? It tells me how much variation in that variable we are extracting using our factor analysis. For example, when it comes to male life expectancy, out of 100% variation, we are extracting 89.4% of that variations, which is pretty good. The bare minimum we want to be 0.7 if you're using eigenvalue approach. So here we are extracting 89.4% of the variation. Here we are extracting, let's say, for natural log of beds, we are extracting 67% out of 100% variation. So that tells me how much variation for each variable we are extracting here. Now, total variance explained here tells me that only one component is there which has eigenvalue of greater than 1. Here the eigenvalue is 8.16. And we are extracting this one component is extracting 81.6% of the total variation among these 10 variables, which is pretty good. 81% is very good amount here. So we can go ahead and retain this one component, but we need to see the other criteria as well. We need to see the variance criteria, retain all the components that account for at least 70% of total variability. So if you see here, the one component itself is accounting for 81%. So we are satisfying kind of second criteria as well, which is again suggesting that we should retain only one component. Scatterplot retain all the components within the sharp descent before eigenvalue levels off, and this criterion is fairly reliable when the number of individuals is greater than 250 and communities are greater than 0.3. So we don't have that big data set here. Okay, we have only 100 cases more or less. So, but again, if you see the eigenvalue Scatterplot, again, it suggests that we should only have one factor, because after one factor, it kind of labels off here. So Scatterplot is suggesting one total variance, explain is suggesting one variable. Our eigenvalues approach is also suggesting kind of one component. So all these three criterion are suggesting one component. But if you go to the residual correlation, we see that there are 18 correlations where the residuals are pretty high. Now, what is this residual? So we need to understand what is reproduced correlation. Now we have our original correlation here, which is based on the raw data, and this reproduced correlation is based on the factor solution we just derived. So it's kind of reverse engineering. We use the factor solution to kind of calculate the correlation between those variables, and if factor analysis has done a good job, this reproduced correlation should match pretty much with the original correlation matrix here, and that's what these residuals do here. That is basically, it is a difference between the observed correlation, which is this one, and the reproduced correlation, which is this one, and that difference has to be less than 0.05. If it is more than 0.05, that means we might need to increase the number of components to explain the variations in all the data that we have. So here we have almost 40% of the correlations where the residual value is greater than 0.05, and that's pretty high. So this pretty much suggesting us that we should go ahead and retain two factors. So that's something we need to keep in mind. So since we have a lot of conflicting kind of observation here when it comes to retaining the number of components, let's go ahead and force two components instead of just one and reperform the factor analysis. So I'm going to go to the analyze here, data reduction factor. Let's go to the extraction. So instead of based on eigenvalue, I would say I'm gonna force the number of factors to 2, and rest of the things are going to be same here. Okay, I'm gonna say okay here. So that's my second factor analysis here, and we just gonna go. We have already gone through this one here. Communities also we have gone through this one. If you see that now this is doing better after forcing second component. As you increase the number of components, then the amount of variation extracted from each variable will keep increasing. That's another thing you have to keep in mind. So it was more than what it used to be. So if you remember here, first one, we have, let's see here, natural log of beds, we only extracted 67% of the variation. But if you come here, we are now extracting 74.8% of the variation because we included the second component. And since we are performing the Varimax rotation here, I'm gonna go to the rotated solution here. So if you see that the first factor when we did not rotate was extracting 81% of the 81.6% of the variation in the data set. But after rotating, we first component is kind of extracting 53.54% of the variation in the data set. Now you need to understand that rotation doesn't change anything. It just redistributes the distributions. I mean the variations among the components. So because this is going to make us more interpretable. So after rotation, the first component is explaining 53.54% of the variation in the data set, and the second component is explaining 33.96% of the data set. So if you go to the reproduce matrix here, after including the second component, we are down to 24% from the 40%, and that's pretty acceptable. So our we have only 11 correlations where the residual value is greater than 0.05, and that should be acceptable. So we're gonna go ahead and retain 2 components. So that's there here. Then once we are done with the number of components here and the amount of variation each component is extracting, we go to the rotated component matrix here. This tells me which factors are loading high on which component. So if you see here, fertility rate, birth rate, life expectancy for male, infant mortality rate, life expectancy for female, and natural log of dogs, they're all loading very high on component 1. Now this is kind of bipolar loading here because we have some high negative and high positive loading. So this is very difficult to name such components here. But if you see here, they're all kind of targeting lifespan of the individual in the country. So probably we can go ahead and say that okay, one component will account for all these 1, 2, 3, 4, 5, 6 factors or 6 variables here, and we can give it a name called healthy lifespan. Again, you need to, when you're naming the factor, you need to make sure that you take into account both the negative and the positive loading. So when you say healthy lifespan, looks like healthy lifespan is better when the male life expectancy or female life expectancy goes up. So is the number of doctors that goes up. But healthy lifespan is better when the fertility rate, the birth rate, and the infant mortality rate goes down. That's how you would interpret that component here. Okay, and the second component will relate to they are loading very high here. So I'm gonna probably go ahead and name them something called economic stature, because they are all related to economic status for the individual in the country. So economic stature could be a good naming, and they're all positively correlated here. Okay, and one thing again, what are these are called factor loadings. What are factor loadings? they are basically the correlation between the factor and every variable. So 0.879 is the correlation between the fertility rate and component 1. So high correlation between the variables and the factors, so they tend to go together. So if you have a lot of high loadings on a particular component, that means these variables, they co-vary, they are highly correlated to each other, and that's why one component is kind of good enough to explain most of the variation in this groupings here. Okay, so factor loadings are nothing but the correlation between the component or the factor and you know, and the variable. And if you square this factor loading and sum it up for that factor, you get the eigenvalue for that factor. So if you square all these loadings, okay, for component 1 and sum it up, you get the eigenvalue, and eigenvalue for factor 1 was 8. Okay, so that's how you get the eigenvalue. So eigenvalue for the second one, again you do the square all this loading on the second one, sum it up, so probably you're gonna get the eigenvalue for the second factor here. Okay, eigenvalue for the second one is 0.59. So that's all. And another, you know, may not be as much of interest to you, but how you get this communalities here. Again, what you do is you see how much this variable is loaded on every factor. So you're gonna, you know, see the loading. So basically, you know, if you, for this variable, if you square the loading on factor 1 and sum it up with the square of loading on the factor 2, you're gonna get the eigenvalue for that variable, and from that eigenvalue you can easily determine the communality. So the formula is very simple. The eigenvalue that you derived here divided by the number of factors, number of variables, which are 10, and the result should be multiplied by 100 to get the communality here. So that's simple formula that you need to keep in mind. So I guess we have pretty much done here. We already named the components, and we have also seen the rotated component matrix here. These two factors, even though we performed the Varimax rotation here, there seems to be some correlation here, but that's not of that much importance at this point in time. So if I go back to my data view here, go to the right here, it has created these two factors here. This was the first factor created before the rotation, and after the rotation we created these two factors. So going forward, these scores, which are the linear combination of all the variables loading in factor 1, is sort of a regression score, and it's like a regression analysis by performing the weighted linear combination of all the variables loaded on that particular factor. Okay, so this factor loadings, we can use it in our future analysis. So if you want to perform MANOVA or multivariate, I mean the multiple regression, we can use these two components instead of those 10 variables, and we can always name them well. So we can say this one is like a, I'm gonna say this one is healthy lifespan, and this one is economic stature. Okay, so if you save this one, so let's say if I save, so this is how you perform the factor analysis. Thank you very much for listening.